Very good afternoon, students.
Good afternoon.
Good afternoon, sir.
So, good afternoon, all. Let us start the discussion without wasting any time. Last class, if you look carefully, we have done the electrolytes of NaCl. There in the electrolytes of NaCl, we have Na plus and Cl minus ions. Using Nelson cell or diaphragm cell, if you do the electrolysis, you will be getting respective chlorine gas and H2 gas and Na plus ions and OH minus ions present in the reaction mixture. They form the respective NaOH. That is how you can prepare the NaOH. You can also prepare NaOH by other cell known as Kastner-Kellner cell. In this cell, what is going to happen is electrolytes of brine you are doing again, that is NaCl gives Na plus and Cl minus. At anode is positively charged, cathode is negatively charged. At anode, the negatively charged chloride ions will be reaching the anode to form respective chlorine gas, and 2 electrons are going to be evolved. That is oxidation occurs at anode, and at cathode we have Na plus and H plus, right? Earlier we have written H plus will take up the electron to form H2 gas. Now Na plus will take up the electron to form Na because the reduction of Na becomes easy in the presence of mercury electrode. The Na will be reactive with mercury to form NaHe. The reduction of Na plus becomes easy in the presence of mercury cathode as amalgam formation takes place. Amalgam formation takes place. So taking this as an advantage, we have just formed Na plus Hg forms NaHg. That NaHg sodium amalgam has been reacting with water to form NaOH again. That sodium amalgam has been treated with water to form NaOH, and H2 gas is evolved along with 2 mercury. Is that clear or not?
Yes, sir.
It is also similar brine solution only. Just we have changed the electrolyte. That is mercury electrolyte. Mercury electrode we have taken. Whenever you take the mercury electrode, the respective reduction of Na plus becomes easy because of the amalgam formation. Based on that, NaOH has been obtained whenever the mercury amalgam has been reacting with water. Right. So after the preparation of NaOH, we have to look at the properties. NaOH is also a white crystalline solid, and it will be acting as a very strong base. It absorbs CO2 from air, forming Na2CO3. Because NaOH dissociates to produce Na plus and OH minus ions. The OH minus will be attacking CO2. Na plus OH minus will be attacking CO2. We have C double bond O. C double bond O. OH minus attacks the carbon, pi electron density moves away. We have C double bond O, C OH and CO minus. This upon loss of H plus, it will form because one more OH minus can pick up this proton. The one more OH minus can try to pick up this proton, and you will form C double bond O minus, and this will develop electrostatic force of attraction with 2 Na plus ions. So Na2CO3 is going to be formed whenever NaOH has been absorbing the CO2, and this was the mechanistic approach. NaOH will be reacting with SiO2 to form Na2SiO3, and it will also react with Al2O3, that is with aluminum. With silicon it will react, or silicon oxide, silicon dioxide will react to form Na2SiO3, which is nothing but sodium silicate. Na2SiO3 sodium silicate is formed. Similarly, NaAlO2 sodium meta-aluminate is going to be formed whenever the reaction occurs with Al2O3. NaOH reacts with SiO2 to form Na2SiO3, which is nothing but sodium silicate. With Al2O3 it forms NaAlO2, which is nothing but sodium meta-aluminate. Sodium meta-aluminate. Right? Is that clear or not?
Yes, sir.
Yes, right.
Yes.
Reaction with the non-metals. No reaction with H2, N2 and carbon. Reaction of NaOH with the boron will lead to the formation of sodium borate. With the silicon, it will form sodium silicate Na2SiO3. With the phosphorus, it forms sodium hypophosphite. NaOH will be reacting with respect to non-metals also. NaOH can also react with different kinds of metals also. NaOH reacts with non-metals like boron, silicon and phosphorus to form sodium borate, sodium silicate and sodium hypophosphite. And different kinds of metals can also be reacting with NaOH. Like with alkali metal, NaOH will not be having any reaction. And different kinds of metals like aluminum, beryllium, zinc, tin, lead, all of them they are going to be reacting to form respective compounds. With aluminum we form sodium meta-aluminate. With the beryllium, sodium berylate Na2BeO2 is going to be formed. With zinc, sodium zincate Na2ZnO2 is going to be formed. With the tin, Na2SnO2, sodium stannite is going to be formed. And with the lead, it will form Na2PbO2, sodium plumbite, and H2 gas is evolved. If you remember, this is a method of preparation of H2 gas also, whatever we have discussed in the hydrogen. Amphoteric metals, they will be reacting with NaOH to release out H2 gas. Along with that, different other respective compounds are going to be formed. NaOH reacts with aluminum, beryllium, zinc, tin, lead to form respective H2 gas. Along with that, sodium meta-aluminate, sodium berylate, sodium zincate, sodium stannite, and sodium plumbite are going to be obtained. Is that clear, students?
Yes, sir.
That's right. Very good. NaHCO3, sodium bicarbonate. Sodium bicarbonate is also called as baking soda. Sodium bicarbonate, that is also called as baking soda. How to prepare it? It is actually prepared. It is obtained by a saturated solution of sodium carbonate with carbon dioxide. It is obtained by a saturated solution of sodium carbonate with the carbon dioxide by treatment of saturated solution of sodium carbonate with the carbon dioxide. So you have Na2CO3 plus H2O plus CO2, that will lead to the formation of NaHCO3. Na2CO3 plus H2O plus CO2, that will lead to the formation of NaHCO3. Yes, Karthik, Na2CO3 is obtained by Solvay's process only. From where you will get Na2CO3? That is obtained from Solvay's process only. Okay, so you can also say NaHCO3 is also obtained by Solvay's process. And upon heating, it releases out CO2 and forms like bubbles, and thus it will be making the pastries fluffy. Like whatever it is also called as baking soda, because in the pastry preparation we'll be adding NaHCO3. Whenever you try to heat it, upon heating, what happens? It undergoes CO2 is lost. Upon heating sodium bicarbonate, upon heating sodium bicarbonate, CO2 is liberated. CO2 is liberated, and thus it will make the pastries fluffy. Because you will be adding respect to NaHCO3 to make different kinds of pastries. Baking soda, whenever you try to add, and you are heating it greater than 100 degrees Celsius, means CO2 is obviously going to be evolved. Okay. Properties, if you try to think of hydrolysis, it will be reacting with water NaHCO3 it will be reacting with water to form NaOH and H2CO3. That means NaHCO3 plus H2O, it will form NaOH and H2CO3. What happens? Na plus plus CO minus C double bond O COH. You are treating this with water, right? H2O. So the lone pair of electron present on oxygen that can try to pick up this proton, leading to the formation of O minus, forming Na plus and C double bond O CO minus CO minus. Along with that, H3O plus is obtained. I can say OH minus from the water picked up the proton. So you will be generating respective OH minus present, H3O plus is there. So Na plus will be reacting with OH minus to form NaOH, and two H plus ions will be coordinating here to form OH minus will develop electrostatic force of attraction with NaOH, and O minus will develop electrostatic force of attraction with H plus. This is nothing but your respective H2CO3. Hydrolysis, if you try to do NaHCO3 upon reacting with water, it forms NaOH and H2CO3. Effect of heat, temperature. Effect of heat, that is, if you try to heat NaHCO3, as I have told you, it will release out CO2. The same reverse reaction is going to happen. Na2CO3 plus H2O plus CO2, they will form NaHCO3, but you heat the crystals of NaHCO3, the carbon dioxide is going to be evolved back and Na2CO3 is obtained. Na2CO3 is obtained. Reaction with acid forms CO2 because weak base will be reacting with strong acid. The strong acid HCl can be reacting with a weak base NaHCO3, forming out NaCl and H2O and CO2. Forming out NaCl and H2O and CO2. Reaction with base can also happen. NaHCO3 can also be reacting with a strong base like NaOH to form Na2CO3 and H2O. Why it will react with a strong base? Because we have C double bond O, CO minus COH. This OH bond is again going to be acidic proton, source of acidic proton. So OH minus from NaOH can pick up this proton, forming C double bond O minus O minus. With not only strong acid, with a strong base like NaOH also, NaHCO3 will react to form Na2CO3 and water. With the strong base, what happens? The OH bond has been cleaved and you get respective carbonate CO3 2 minus obtained. These are the different kinds of reactions of NaHCO3, that is upon heating, upon treating with acid or base, upon hydrolysis. What is going to happen? We have studied with respect to sodium hydrogen carbonate. It is also called as sodium hydrogen carbonate. All right. NaHCO3, sodium bicarbonate or sodium hydrogen carbonate baking soda. If you try to think of its uses, in the preparation of baking powder, it will be used. It is also used as an antacid in medicine, that is removing acidity. If you remember, in the antacid, before discovering the chemicals like Zantac, what we have done, whatever the acid, extra acid produced in the stomach, that has been removed by taking a base. We have taken bases like NaHCO3. But NaHCO3, when compared to NaHCO3, aluminum hydroxide and magnesium hydroxide are better. Why?
Because sodium is more soluble.
Yeah, because NaHCO3 is more soluble and making the stomach alkaline. Because of making the stomach alkaline, what happens? It will trigger out more acid production. But these two are actually controlling the only
Symptoms.
acid which is obtained. But we have to stop the production of acid, which is done by respective Zantac. Yes or no? Histamine is actually the chemical which will go and bind to the receptor present on the stomach wall. Because of that only, you will have the release of acid. Nowadays, we are taking drugs which are controlling the binding of histamine with the respective receptor. But we can also control the drug like there are some other drugs which can disturb or which can control the concentration of histamine. Antacid, what it is going to do? It will try to act as a competitor. It will go and stick on the wall, like on the receptor where the histamine is going and binding. But if I can take a drug which can decrease the histamine, which can decrease the concentration of histamine. Then also, like the fuel itself has been removed means obviously you will not be having the more production of acid. Like that, different drugs has been synthesized. Na2CO3, sodium carbonate or caustic soda. Preparation, if you try to look, it is always process. Understand this point carefully. See, first you are taking NaHCO3. Whenever you trying to heat, you will get Na2CO3 plus H2O plus CO2. When compared to ammonium hydrogen carbonate, that is, the ammonium hydrogen carbonate has been treated with NaCl to form NH4Cl and NaHCO3. The ammonium hydrogen carbonate is obtained by the reaction of ammonia with the water and carbon dioxide. This carbon dioxide is actually obtained by the reaction of, like by heating CaCO3, you will be generating respect to carbon dioxide. And the crystals of NaHCO3 were heated to produce Na2CO3. Understand what we are trying to say. First, you will try to take the saturated solution of ammonia. Saturated solution of ammonia is heated with carbon dioxide. Carbon dioxide from where you will obtain? By heating CaCO3, you will get carbon dioxide to form ammonium hydrogen carbonate. This ammonium hydrogen carbonate is converted to sodium hydrogen carbonate by treating with NaCl. That sodium hydrogen carbonate crystals, whatever you are going to have, those crystals you can heat. By heating those crystals, you will produce Na2CO3 and H2O and CO2. This is nothing but the Solvay's process. Like when you try to heat 2 NaHCO3, you will get Na2CO3 plus H2O plus CO2. Potassium bicarbonate KHCO3 cannot be prepared by Solvay's process as it is soluble in water. KHCO3 is soluble in water, whereas NaHCO3 is not soluble in water. The NaHCO3 will have Na plus and HCO3 minus ion. The less solubility of NaHCO3, the insoluble NaHCO3 that has been taken out, and the crystals of NaHCO3 were heated to produce Na2CO3. The crystals of NaHCO3 were heated to produce Na2CO3. This is nothing but your Solvay's process. Yes. Clear or not, Karthik? NaHCO3, that crystal, whatever it is there, if you try to heat the crystal of NaHCO3, you will get Na2CO3 and H2 and CO2. The ammonia and carbon dioxide, whatever left out, they are again recycled. And because of recycling, again the reaction is going to be done. Like that, you will be producing respective NaHCO3. If you don't heat the crystals of NaHCO3, that is how the preparation of NaHCO3 can also be done. If you try to heat the crystals of NaHCO3, you will get Na2CO3. We have prepared NaHCO3 by this reaction earlier, by the reverse reaction, Na2CO3 plus H2O plus CO2. Yes or no? Saturated solution of, yes, saturated solution of ammonia is shared with carbon dioxide to form ammonium hydrogen carbonate. Ammonium hydrogen carbonate react with NaCl to form sodium hydrogen carbonate. The sodium hydrogen carbonate upon heating forms Na2CO3 and NH4Cl is treated with CaO to form CaCl2 and ammonia and H2O. This ammonia and the CO2, which are byproducts, they will be recycled again and again to produce more and more amount of NaHCO3. From that NaHCO3, we get more and more amount of Na2CO3, sodium carbonate. Potassium bicarbonate you cannot prepare as it is soluble in water. Properties, if you think of Na2CO3, efflorescence, Na2CO3.NH2O, when exposed to air, it gives a 9 out of 10 H2O molecules. When Na2CO3.10H2O, upon heating it, it will give 9 out of 10 H2O molecules, but the temperature you have to maintain, that is up to 373 Kelvin. If the temperature is maintained greater than 373, then what happens? The Na2CO3 dot H2 or whatever you have, right? That one molecule is also going to be lost. One molecule of H2 is also going to be removed, and we get anhydrous. The process of efflorescence, this process is called as efflorescence. Hence, washing soda loses weight on exposure to air. On exposure to hot air, washing soda will be losing the weight because the Na2CO3.NH2O up to 373 Kelvin, if you try to heat, you will get Na2CO3.H2O, 9 molecules are lost. And if you try to do the hydrolysis, what happens? Na2CO3, if you try to do the hydrolysis, Na2CO3 will have 2 Na plus and CO3 2 minus, that is C double bond O minus O minus. The CO3 2 minus, upon treating with water, it forms what? Upon treating with water, 2H2O. It will form OH, C double bond OH, along with the 2 OH minus is released. These 2 OH minus and 2 Na plus, they will react to form 2 Na plus 2 OH minus will be forming 2 NaOH. That means what I can say, Na2CO3 plus 2H2O forms H2CO3 plus 2 NaOH. Can I write the reaction like this? Na2CO3 plus 2H2O, it is forming H2CO3 plus 2 NaOH. This was the reaction. Whenever you try to do the hydrolysis of sodium carbonate, you will be getting respective H2CO3, carbonic acid, and NaOH is going to be evolved. NaOH is also going to be produced. Aqueous solution of Na2CO3 is alkaline in nature. Why? Because of production of NaOH, which is a strong base. Aqueous solution of Na2CO3 is alkaline in nature because of the production of NaOH, which was a strong base. Right? Na2CO3 will give 2 Na plus and CO3 2 minus. CO3 2 minus react with water to form H2CO3, and 2 OH minus are going to be evolved. Uses for making fusion mixture, Na2CO3 and K2CO3, which is used in salt analysis. The uses of Na2CO3, if you try to think of, Na2CO3 is used in the fusion mixture as well as like soap powders, caustic soda, glass. In all these preparations, this is going to be used. Na2CO3 is used in different purposes, and these uses we have to remember. Uses we have to remember no other way. This is how the respective Na2CO3 is going to be useful. KHCO3 cannot be prepared by solvent process due to instability, high lattice energy, high solubility in water, high polarizing power of K+.
High solubility in water.
Solubility in water.
High solubility in water, right? Very good. On exposure to air, how many water molecules are lost by washing soda? Na2CO3 or NaCO3?
9. 9.
9 water molecules. Right? Then you have next commercially important compounds, calcium oxide of quicklime, CaO. How is this obtained?
By heating calcium carbonate.
Calcium
By
carbonate
heating
heating.
calcium carbonate to very high temperatures like 1070 to 1270 Kelvin. Preparation by heating limestone, that is CaCO3 at 800 to 1000 degrees Celsius, or you can note the temperature in this function. CaCO3, when you heat to 1070 to 1270 Kelvin, in this range, you will generate CaO plus CO2. You will generate CaO plus CO2. This was how you are going to prepare the respective quicklime. This is your quicklime. Yes or no? This is the method of preparation of quicklime. By heating limestone, that is CaCO3 at very high temperature, you are going to generate quicklime and CO2. And this quicklime, that can be reacting with the water to form what?
Calcium hydroxide.
CaOH taken twice. It is also called as slaked lime or calcium hydroxide. You can study this as a property of CaO. Yes or no? Calcium oxide or quicklime properties. If you think of action of water, quicklime upon treatment with water, it forms laker lime, CaOH taken twice. Suspension of CaOH taken twice in water is called as milk of lime, whereas solution of CaOH taken twice in water is called as lime water. Understand this point carefully. Suspension and solution. What was the difference between suspension and solution?
Suspension is heterogeneous mixture and solutions.
Suspension means heterogeneous mixture, obviously. And what is the particle size? Greater than
Greater than
1000 nanometers.
10,000 nanometer.
Solution means
Homogeneous mixture.
Mixture.
yes, less than 1 nanometer particle size. Particle size. Okay, suspension is heterogeneous. Solution is homogeneous. So suspension of CaOH taken twice in water, that is called as milk of lime, whereas solution of CaOH taken twice in water, that is called as lime water. Basic nature, CaO, metallic oxides are generally basic in nature. Metallic oxides are generally basic in nature. So CaO is a basic oxide, so that will be reacting with acidic oxides. So acidic oxides are non-metallic oxides like CaO react with SiO2 to form CaSiO3 calcium silicate, and CaO react with P4O10. It will also form Ca3PO4 taken twice calcium phosphate. Yes or no? And a reaction with carbon, CaO plus 3C upon heating forms calcium carbide CaC2. Along with that, CO is going to be evolved. CaO plus 3 carbon gives CaC2 plus CO. So calcium carbide will have what type of structure? Like Ca plus 2 will have electrostatic force of attraction with a C minus ion, and this is how the structure can be understood. Ca plus 2 will be having electrostatic force of attraction with C minus 2, where the carbon-carbon triple bond is there and each carbon contains negative charge. That will develop electrostatic attraction with the Ca plus 2, which is nothing but calcium carbide. Yes or no?
Yes.
Yes.
Sir.
Uses, if you try to think of, what are the uses of CaO?
Whitewash.
That is also prepared. It is used in the manufacturing of a bleaching powder, cement, glass, calcium carbide, for making soda lime, as a drying agent for ammonia and C2H5OH. It is also used as a basic lining in surfaces, in furnaces. In different furnaces also, you are going to use CaO as the basic lining, and different types of reactions can also be understood with respect to this perspective. Like we can try to think of a reaction like CaCO3 upon heating gives A and B. Like we can think of reaction CaCO3 upon heating gives A and B. And I'll give first B is absorbed by NaOH. A reacts with carbon to form G and H. B is absorbed by NaOH, and A reacts with a carbon to form G and H. G upon hydrolysis forms C and D. G upon hydrolysis forms C and D. C turns lime water milky, and D can react with NaNH2. D upon treatment with Fe or copper at very high temperature form E. E upon treatment with H forms F. E upon treatment with H forms F. You try to figure out what are A, B, C, D, A, B, C, D, E, F, G, H. I have given a question like this: CaCO3 upon heating forms A and B. CaCO3, if you try to heat, you will get what?
CaO and CO.
CO2.
And what I have told you, A and B are obtained whenever you try to heat a CaCO3. B is absorbed by NaOH and A reacts with a carbon to form G and H. Which will be absorbed by NaOH?
CO2.
CO2.
CO2. So B is CO2 and A is CaO. B is CO2 and A is CaO. Now B is absorbed by NaOH, that is why B is CO2, and A reacts with carbon to form G and H. A is CaO. CaO reacts with carbon to form what?
Ca2C and CO.
CaC2 and
CaC2.
Carbon monoxide.
CaC2 and CO. Yes or no? CaO plus 3C will be forming like CaC2 plus CO. So what are G and H? These are G and H. G upon hydrolysis forms C and D. C turns lime water milky and D can react with NaH2. This is G and H. G upon hydrolysis forms a C and D.
Ethyl.
So what is G among this? G is CaC2. Because CaC2 upon hydrolysis will form what? CaOH
CO
taken twice
and ethyl.
plus C2H2. Yes or no? This is G means automatically CO is going to be H. G is CaC2, H is CaO. CaC2 is your G. G upon hydrolysis forms C and D. C turns lime water milky. What is C then? CaOH taken twice. And what is D? D is nothing but C2H2. And D can react with NaNH2. C2H2 can react with NaNH2. Yes, because acetylene has acidic hydrogens. And D upon treatment with copper or iron at very high temperature for me. C2H2 will be reacting with copper or iron at a very high temperature will form what? Benzene. Cyclic polymerization occur or not? Like cyclic trimerization. So form C, E is nothing but a benzene. E upon treatment with H. What is H? E upon treatment with H. E upon treatment with H forms and H in the presence of HCl. H in the presence of HCl forms F. What is F?
Benzaldehyde.
Respective benzaldehyde. Like that, you can correlate different types of things and try to write down the different types of reactions, like organic, inorganic chemistry can also be combined. Such complex questions can also be. You can understand such complex questions, then you will get more knowledge, right? CaOH taken twice calcium hydroxide or Slagle lime. How is this obtained? CaOH taken twice is actually obtained when you try to treat CaO with water, that is hydrolysis of quicklime produces calcium hydroxide. Quicklime, if you try to do the hydrolysis, you will be producing Slagle lime or calcium hydroxide. Properties, if you try to think of, CaOH taken twice will react with carbon dioxide. CaOH taken twice will react with carbon dioxide to form CaCO3, which will be milky in nature. CaCO3 upon excess of CO2 will form CaHCO3 taken twice, where milkiness disappears. Lime water turns milky upon passing CO2 through CaOH taken twice. Lime water turns milky on passing CO2 gas. CaOH taken twice upon reacting with CO2, it forms a milky white colored. Why? Due to the formation of CaCO3. That CaCO3 upon treatment of excess of CO2, it forms CaHCO3 taken twice. which is actually soluble. That is why excess of CO2 you should not add where the milkiness is going to be disappearing. Action of chlorine. The calcium hydroxide will be reacting with the chlorine below 35 degrees Celsius to form bleaching powder, where the major component of bleaching powder is CaOCl2, where in CaOCl2 we have electrostatic force of attraction with Ca plus 2 and OCl minus and Cl minus ions. But the total composition can be right CaOCl2 dot CaCl2 dot CaOH taken twice dot H2O. You can write the total composition in this manner. You can write the total composition in this manner. Yes or no? CaOH taken twice upon treatment with chlorine below 35 degrees Celsius, it forms bleaching powder, where the major component is CaOCl2, where you have Ca plus 2 and OCl minus ion along with Cl minus, and water is obtained. If you try to heat a calcium hydroxide with chlorine up to red heat, a very high temperature, you will form CaCl2 and H2 and O2 gas is evolved. Whenever you try to heat up to red heat, O2 gas is going to be evolved, right? Uses, if you think of calcium hydroxide for softening or hot water, where you have used the students?
Clark's method.
Like temporary hardness or permanent hardness? Temporary hardness. Yes or no? Yes. For softening of hot water, for purification of sugar and coal gas, and also in the manufacture of bleaching powder, caustic soda and soda lime, this calcium hydroxide is going to be used. As I was saying again and again, you have to remember the uses. Calcium sulfate or dead burnt plaster. So calcium sulfate or dead burnt plaster, in this what category you are going to have? Calcium sulfate or dead burnt plaster, what is that?
Gypsum.
Like how we are going to prepare it? CaSO4 dot 2H2O is nothing but calcium sulfate. How you can prepare it means you can actually heat by the action of H2SO4 on calcium chloride. CaCl2 plus H2SO4 gives HCl plus CaSO4 plus H2O plus O2, and that CaSO4 dot 2H2O, that upon heating will form CaSO4 taken twice dot H2O, which is nothing but plaster of Paris also. CaSO4 dot half H2O is nothing but plaster of Paris also. So we have different types of reactions. Like gypsum is what? CaSO4 dot 2H2O. What is gypsum?
CaSO4 2H2O.
CaSO4 dot 2H2O is nothing but your gypsum. So preparation, let us look at now. CaSO4 dot 2H2O, the calcium sulfate is actually obtained by treating calcium chloride with H2SO4. Whenever you treat calcium chloride with H2SO4, you will get HCl. Ca plus 2, Cl minus ions are there, H plus SO4 minus 2 ions are there. CaSO4 is going to be formed along with the release of 2 moles of HCl, and H2O and O2 is also evolved. CaSO4 dot 2H2O, whatever the calcium sulfate, hydrated calcium sulfate you have, that when you try to heat up to 120 degrees Celsius, you will lose 3 moles of H2O from CaSO4 dot 2H2O. Like if you take 2 moles of gypsum, 2 CaSO4 dot 2H2O will have 4 H2O molecules. When you heat up to 120 degrees Celsius, out of 4 H2O, 3 H2O is going to be lost, and you will have CaSO4 taken twice dot H2O, or you can say CaSO4 dot half H2O. With respect to 1 CaSO4, you have half H2O, or with respect to 2 CaSO4, you have 1 H2O. This is nothing but a hemihydrate of calcium sulfate, which is also called as your plaster of Paris. Hemihydrate of calcium sulfate is called as plaster of Paris, and that plaster of Paris, whenever you try to heat further up to 200 degrees Celsius, you will get a CaSO4 anhydrous. That CaSO4 anhydrous, that is also called as dead burnt plaster. CaSO4.2H2O is gypsum, CaSO4.of-H2O is plaster of Paris, CaSO4 anhydrous is dead burnt plaster. Is that clear or not?
Yes, sir.
And CaSO4 will be reacting with ammonia, solution of ammonia in the presence of carbon dioxide to form ammonium sulfate. This ammonium sulfate is also going to be formed. Ammonium sulfate, which will be acting as an important fertilizer. Ammonium sulfate will be acting as an important fertilizer. Uses, if you try to think of the uses, CaSO4 calcium sulfate is used in the preparation of plaster of Paris. Anhydrous CaSO4 is used as drying agent because it will try to remove all the H2O from the respective fabrics, and that is why, since it is removing H2O, it is also used as drying agent. It is also used as drying agent, right? CaSO4.of-H2O, calcium sulfate hemihydrate or plaster of Paris. How is this obtained, students? When you heat gypsum up to 120 degrees Celsius, you will get a plaster of Paris. Gypsum heat to up to 120 degrees Celsius, you get POP, plaster of Paris. That means in the gypsum, like 2 moles, if you take 2 CaSO4.2H2O, out of 4 H2O, 3 H2O has been removed out, and only we are left out with 1 H2O. So it is obtained when gypsum is heated at 120 degrees Celsius. 2 CaSO4.2H2O gypsum, upon heating up to 120 degrees Celsius, it will lose 3 H2O molecules with 2 moles of gypsum, and you will form CaSO4 taken twice dot H2O, or you can also write as CaSO4.of-H2O. This is nothing but your respective plaster of Paris. Is that clear?
Yes, sir.
And plaster of Paris, what was the applications or uses?
Roof
Properties.
sealing.
Yes, sealing. It is actually a white powder. It has a property of setting to hard mass. It becomes hard when a paste of water is allowed to stand aside for some time. Plaster of Paris, when you try to add water to POP and you set aside for some time, it becomes hard mass. When it is heated at 200 degrees Celsius, calcium sulfate or dead burnt plaster is formed. CaSO4.of-H2O, upon 200 degrees Celsius heating, it forms CaSO4 anhydrous. Loss of half H2 occurs. It is nothing but dead burnt plaster. It is nothing but, it is also used in the dead burnt plaster preparation. Uses, if you go with, in making statues and toys, different uses are there. In making statues and toys, in ornamental ceiling designs and linings, in plastering for fractured bones, like in the medicine also it is used. Yes, for the orthopedician, like for the fractured bones, this POP is also used. Okay. So in making statues and toys, in ornamental ceiling designs, in plastering for fractured bones, this, because it becomes hard, right? So whatever the displacement, bone displacement happened or a slight broken, in that case, if it is fixed, the bone is fixed in the same position for longer days, means it becomes again set. This is nothing but your calcium sulfate hemihydrate or plaster of Paris. Then the last commercially important compound of S block is cement. Like, it is not a commercially important compound, it is like a mixture of silicates and aluminates. Cement is actually a light grey in color. It is a homogeneous mixture of silicates and aluminates, and it is used in the building purposes mainly. It is a light grey, heavy, fine powder. It is a homogeneous mixture of silicates and aluminates of calcium. Like essential constituents, lime, silica, alumina. These are the essential constituents of cement. And raw materials, if you think of like limestone, clay, alumina, Like a clay will have respect to Al2O3 and silica. And you can also take gypsum. Gypsum is also added to in the process of making cement. So we'll add CaCO3, limestone, clay, which provides Al2O3 and SiO2, gypsum, CS4.H2O. All these are going to be added in the manufacturing process of cement. Why gypsum is added in the manufacturing of cement? To slow down the process of setting. Cement also becomes hard. If you try to add some water to cement, it will also become hard if you leave it for some time. That time, to increase the time of becoming hard, gypsum is added. And why the cement becomes hard? Because of recrystallization of the respective crystal atoms, crystal lattice. Recrystallization. Due to recrystallization of the atoms, the setting of cement is going to happen. To slow down the process of setting of cement, gypsum is added. What are the lime, clay, and gypsum? These are the raw materials, and you have to take these raw materials and then only convert the respective, produce the respective cement. Yeah, as I was saying, raw materials are limestone. Limestone will be producing CaO, calcium oxide. Clay will produce Al2O3 and SiO2. And gypsum is CS4H2O. What is the role of gypsum?
Bring down of recrystallization.
Yes, slow down the setting of cement. That is, gypsum is used in cement to retard or slow down the setting process. That is, increase the time of setting. Because instantly, if I try to add water and instantly it becomes hot, then obviously it is not so useful in the preparation purposes. So that is why you are going to add gypsum to slow down the retardation process, to slow down the setting process or retard the setting process. Composition of cement, different compositions are there in this fashion. But for a good quality cement, what you can say? For a good quality cement, ratio of silica and alumina should be 2.5 to 4. Ratio of silica and alumina should be 2.5 to 4. That is like percentage of silica and percentage of alumina. If you take the ratio, you will get in between 2.5 to 4. Ratio of lime with other oxides should be close to 2. Ratio of CaO with all other oxides, that should be close to 2. Ratio of silica and alumina, that should be lying in the range of 2.5 to 4. Then only we can say that particular cement has a good quality cement. Is everything clear so far?
Yes, sir.
Yes, right. So these are all the commercially important compounds of your group 1 and group 2 elements. And then comes the next concept like solubility. If you try to compare solubility, like dissolves in like, ionic compounds are soluble in polar solvent like water. Non-polar covalent compounds are more soluble in non-polar solvents like benzene. Like dissolves in line. Ionic solvents, if you take, like ionic compounds, if you take, they are going to be more soluble in polar solvent because ionic compound has polar nature, and polar solvent like water also have partial positive on hydrogen, partial negative on oxygen. The polar nature of ionic compound will developing electrostatic force of attraction with the polar H2O molecule, making the good electrostatic force of attraction developed means obviously soluble. Non-polar covalent compounds are more soluble in non-polar solvents like benzene, CCl4. Polar compounds are soluble in polar solvents. Non-polar compounds are soluble in non-polar solvents. And factors affecting solubility. Solubility is directly proportional to hydration enthalpy. Why? because a particular ionic compound is there, Na plus Cl minus. If you try to add it to water, it forms Na plus ions, Cl minus ions, Na plus also highly hydrated, Cl minus also highly hydrated. Let us say that case. Hydration enthalpy is the amount of energy evolved when the respective ionic compound is added to water. That means hydration occurred with respect to Na plus as well as with respect to chloride. The Na plus is also surrounded by many H2O molecules. Cl minus also surrounded by many H2O molecules. More is the extent of hydration, more is the solubility. More is the extent of hydration, more is the solubility. And solubility is inversely proportional to lattice energy. Solubility is also inversely proportional to lattice energy, because if NaCl has more electrostatic force of attraction, then the dissociation of NaCl into Na plus and Cl minus ions, that is not going to happen. Two things are there. Whenever the lattice energy is stronger, then the ionic compound will not dissociate to form respective ions. When the hydration enthalpy is greater, greater will be the solubility. When the lattice energy is weaker, then the solubility is greater, because if the lattice energy is stronger, then the compound wants to be in the solid stage, not in the respective ionic stage. Is that clear or not?
Yes, sir.
So this is how you can understand solubility, and you can compare the same. Hydration energy, the amount of energy released in the hydration of 1 mole of ionic crystal, that is nothing but hydration energy. Lattice energy is the amount of energy required to break the lattice of 1 mole of ionic compound, that is said to be lattice energy. If we have NaCl, Na plus Cl minus electrostatic attraction, if I have to break, that is nothing but lattice energy. If Na plus ions are surrounded by water, Cl minus also surrounded by water, then some amount of energy is released. That energy is nothing but hydration energy. Solute NaCl, solvent water. NaCl is ionic compound. Solvent is water, which is again polar solvent. Like it dissolves in like. So Na plus ions, Cl minus ions. This Na plus develops ion dipole attraction or not? Between Na plus and H2O, what type of attraction is there? Ion dipole attraction. Between Cl minus and H2O, what type of attraction is there? Again, ion dipole attraction. Na plus and Cl minus, they have electrostatic force of attraction, and that is nothing but lattice energy. You can see this as a field or not, because there is no overlapping of atomic orbitals. In the ionic bond, there is just an electrostatic force of attraction, like Na plus. Around Na plus, we have electric field. Around Cl minus, we have some other field. Those electrostatic force of attraction present between Na plus and Cl minus, that is nothing but your lattice energy. If this is more hydrated, Na plus is more stabilized, more soluble. If the Cl minus more hydrated, more stabilized, more soluble. If the lattice energy is stronger, then I cannot break it, so less soluble. Understood or not?
Yes, sir.
Yes. Factors affecting hydration energy and factors affecting lattice energy are same. So hydration enthalpy, that is also decided based on charge density. That means hydration energy is directly proportional to product of charges, inversely proportional to sizes. Lattice energy also same. Lattice energy also directly proportional to product of charges, inversely proportional to sizes. So hydration enthalpy and lattice energy. Hydration enthalpy directly proportional to charge of cation and charge of anion. Hydration enthalpy inversely proportional to size of ions. Lattice energy also same. Directly proportional to charge of cation and charge of anion, inversely proportional to size of ions. Then how to decide which is dominant? Like if lattice energy is dominant, then solubility is less. If hydration enthalpy is dominant, then solubility is more. How to decide lattice energy is dominant or hydration enthalpy is dominant? That is decided based on the type of ions. Okay. Case number 1, hydration enthalpy greater than lattice energy means what? Soluble. The respective salt is going to be more soluble. If lattice energy greater when compared to hydration, then sparingly soluble or insoluble. Hydration enthalpy greater than lattice energy means soluble. Lattice energy greater than hydration enthalpy means sparingly soluble or insoluble. This is how you can understand solubility. Solubility in a group, you try to compare. Understand this point carefully. If common ion is smaller, then lattice energy is dominant. If the common ion is smaller ion, lattice energy is going to be the dominant factor. F minus, O2 minus, OH minus, Li plus, Na plus, Be plus 2, Mg plus 2, Ca plus 2, Sr plus 2, Ba plus 2. The group 1 cations except K plus, Rb plus, Cs plus, F minus, O2 minus, OH minus, these are the most important example. If the common ion is smaller ion, then which is dominant among hydration enthalpy and lattice enthalpy?
Lattice enthalpy.
Lattice enthalpy is dominant. Yes. Example you try to compare here. Li2O, Na2O, K2O, Rb2O, CS2O. You first listen. Na2O, Li2O, Na2O, K2O, Rb2O, CS2O. So in all these, which is the common ion? O2 minus is the common ion. O2 minus is a smaller ion. If these are set of common ions which you have to remember. O2 minus smaller ion. Smaller ion. So which is dominant? Lattice energy is dominant. So compare lattice energy now. Lattice energy is dominant. Lattice energy Li plus, Na plus, K plus, Rb plus, Cs plus. Charge is everywhere same. Only thing is size. So when you go from Li2O to CS2O, what happened to size? Size is increasing. If size increases, what happened to lattice energy?
Decreases.
Size increasing, so lattice energy is decreasing. Lattice energy decreasing means solubility.
Increases.
Solubility is directly proportional to hydration enthalpy and inversely proportional to lattice energy. So lattice energy is actually decreasing when you go from Li2O to CS2O. Lattice energy, why it is decreasing? Because size is increasing. Since the lattice energy is dominant, so you have to decide based on lattice energy only, not hydration enthalpy. You don't need to consider hydration enthalpy. Based on lattice energy, you can say lattice energy is decreasing, so solubility will be increasing. Understood or not?
Sir.
You will get confused. If you compare hydration enthalpy, you will get reverse order. Hydration enthalpy, if you try to compare, hydration enthalpy is also having the same trend. Hydration enthalpy is also decreasing from Li2O to CS2O. Because of decrease in hydration enthalpy, solubility is going to be decreasing. But which is dominant? Lattice energy is dominant. Why? Because the ion is smaller ion. When the ion is smaller ion, it will develop more charge density. Thereby, lattice energy is going to be the dominant factor. Whenever we have large ions, hydration enthalpy is dominant. If the common ion is larger, then hydration enthalpy is dominant. Like whenever we have carbonate, sulfate, nitrate, ClO4 minus, Cs plus, Br minus, I minus, S minus 2, then which is dominant? Hydration enthalpy is dominant. Example, you take the example of CSF, CSCl, CSBr, CSI. Everywhere you have Cs plus F minus, Cs plus Cl minus, Cs plus Br minus, Cs plus I minus. Common ion is what? Common ion is Cs plus, that is large ion. So what happened to the size? Cs, like charge is same, Cs plus I minus, everywhere plus 1 minus 1 charge is same. What happened to the size? Size is increasing. F minus, Cl minus, Br minus, I minus. If you remove the common ion, with respect to other ion, what happens? Size is increasing. Size increasing means what happened to hydration enthalpy?
Decreases.
Decreasing. Hydration enthalpy decreasing means what happened to solubility? Solubility is going to be decreasing because hydration enthalpy is dominant factor if the common ion is larger ion. Everyone got this or not? If the common ion is larger ion, hydration enthalpy is dominant. If the common ion is smaller ion, then only lattice energy is dominant. The same, whenever you trying to compare the respect to solubility of hydroxides of alkaline earth metals, OH minus, you take which is the dominant factor? Lattice energy as a dominant factor. When you try to look at the solubility of carbonates or sulfates, you take hydration enthalpy as dominant and then try to give the order. Size is increasing, hydration and enthalpy decreases, so solubility will be decreasing. Solubility for compounds of P and D block elements, that is in a period, like if you take solubility for the P and D blocks, AgF, AgCl, AgBr, AgI, there you have to go with this order. Solubility is inversely proportional to covalent character. Solubility is inversely proportional to covalent character. AgF, AgCl, AgBr, AgI. Everywhere we have same charge. Ag plus minus 1, plus minus 1. F minus Cl minus Br minus I minus. What happened to the size of anion? F minus Cl minus Br minus I minus. Size of anion is increasing. Size of anion increasing means what happened to covalent character?
Increases.
For the same cation, large size anions have more covalent character. So covalent character and solubility, they are inversely proportional. Because more covalent character, less is the ionic character. Less is the ionic character, less is the respect to solubility. So solubility is going to be decreasing. So AgI is like if you go with the respect to covalent character, AgI is going to be having more covalent character. So solubility is going to be least for AgI. When you go from AgF to AgI, size of the anion increases, covalent character increases, solubility is decreasing. NaCl, MgCl2, AlCl3, plus 1, minus 1, plus 2, minus 1, plus 3, minus 1, charge is differed. So, like whenever you try to think of Cl minus is the same ion, charge is differed, Na plus, Mg plus 2, Al plus 3, charge of cation increasing, so covalent character increases. Covalent character increasing means solubility decreases. So solubility, which is more soluble? NaCl is more soluble than MgCl2, then AlCl3. Here, this is solubility, AgF, AgBr, AgCl, AgBr, AgI, because solubility is decreasing. Got it or not?
Sir.
Yes. After the solubility, for large size anion, small size anion, like large size common ion, small size common ion, and then P and D block elements. Then you can look at the thermal stability. Thermal stability of a compound having polyatomic anion. Thermal stability you are going to compare. Generally asked question, which of the following are thermally stable? Polyatomic anion, like all these are polyatomic. Here OH minus and CO3 minus are in the same group. Understand this carefully. Polyatomic anions, CO3 minus, sulfate, OH minus, O2 minus, O2 minus, all these are polyatomic anions. The thermal stability is inversely proportional to polarizing power. If the polarizing power is greater, thermal stability is lower. If the polarizing power is lesser, thermal stability is more. You can write down that order. Thermal stability is inversely proportional to polarizing power. CaCO3 upon heating forms CaO and CO2. Thermal stability is inversely proportional to polarizing power. Polarizing power means like charge density, it is directly proportional to charge density, charge of cation by size of cation. You try to compare BeCO3, MgCO3, CaCO3, SrCO3, BaCO3. So polarizing power is directly proportional to charge density. So greater the charge, like everywhere you have plus 2, everywhere you have respect to carbonate CO3 2 minus. CO3 2 minus is a polyatomic anion. So thermal stability inversely proportional to polarizing power. Charge is same everywhere. So you have to compare with respect to size. Where the size is going to be larger? Ba plus 2.
Where?
Ba plus 2 large size means obviously small is the polarizing power. Be plus 2 to Ba plus 2. What happens? Size is increasing. Size increasing means polarizing power.
Decreases.
Polarizing power decreases. Polarizing power decreasing means
Thermal stability decreases.
decreases or increases?
Increases.
Thermal stability is inversely proportional to polarizing power. We have compared polarizing power first. Thermal stability is inversely proportional to polarizing power. Polarizing power is decreasing because of increase in size. Because of decrease in polarizing power, the thermal stability is increasing. So BeCO3 to BaCO3, thermal stability is increasing. Same with respect to nitrates, lithium nitrate to cesium nitrate, what is going to happen? Thermal stability is increasing. These are very logical points, understand this. Thermal stability, questions will be asked. Thermal stability, compare which of the following are more thermally stable, like that. Thermal stability is inversely proportional to polarizing power. Polarizing power directly proportional to charge density. So obviously based on that, you will compare greater the thermal greater the polarizing power, lesser is the thermal stability, or lesser the polarizing power, greater the thermal stability. Right?
Yes, sir.
Yes. Next important points, LiHCO3 and group 2A bicarbonates. They do not exist in solid state. Why? Because LiHCO3 and group 2A bicarbonates has more charge density and thus highly hydrated, and thus hydration enthalpy is dominant. Because hydration enthalpy is dominant, if lattice energy is dominant, then only they will exist in the solid state, right? If lattice energy is the dominant factor, then only they can exist in the solid state. If hydration enthalpy is the dominant, then they will be existing in the aqueous solution only. That is why LiHCO3 and group 2A bicarbonates do not exist in solid state. Carbonates, sulfates, and hydroxides of sodium, potassium, rubidium, and cesium do not decompose at high temperature, they only melt. Decomposition of carbonates, sulfates, and hydroxides of sodium, potassium, rubidium, and cesium, that is not happening. They only melt. If you give high temperature, they will only melt. They are not decomposing. Whereas carbonates, sulfates, hydroxides are remaining, they will decompose. Those decompositions we'll see. BeCO3 is kept in CO2 atmosphere due to less thermal stability. Why it is less thermally stable? BeCO3 is having less thermal stability due to
More covalent character.
high polarizing power. Okay. Because with respect to polarizing power only, we will compare all the thermal stability. Obviously, again, covalent character can also be explained based on the polarizing covalent character. Again, we explain based on polarizing power only. Thermal stability inversely proportional to polarizing power. Wherever you have more polarizing power, like more charge density, there obviously less is thermal stability. So because of less thermally stable, BeCO3 decomposes to BeO and CO2. If already it is present in atmosphere of CO2, then because already CO2 is there, the decomposition is not going to happen greatly. Right? And previously we have discussed what thermal stability of compound having polyatomic anions. Yes or no? Thermal
Yes,
stability
sir.
of compound having polyatomic anion, that is inversely proportional to polarizing power. We can also have thermal stability of compound having monoatomic anion like H minus, O2 minus, only one atom is there, H minus, oxygen with 2 minus charge, F minus, Cl minus, N3 minus. There you will have thermal stability directly proportional to lattice energy. Understand these differences carefully. With a small size common ion, lattice energy is dominant. With a large size common ion, hydration enthalpy is dominant if you compare solubility. If you are talking about thermal stability, for a polyatomic anion, thermal stability inversely proportional to polarizing power. With a monoatomic anion, thermal stability directly proportional to lattice energy. Thermal stability directly proportional to lattice energy. Lattice energy again directly proportional to charge of the ions and inversely proportional to size of ions. Directly proportional to charge of ions and inversely proportional to size of ions. Thus, the stability of oxides of 1A is less when compared to 2A. Stability of oxides of 1A, that is going to be less when compared to 2A. Why? We take oxide La2O, Be2O, La2O, BeO, La2O, BeO. La2O has Li plus 1 and O minus 2. Be2O has Be plus 2 and O minus 2. You should not compare lithium has 2 Li plus, so 2 into plus 1 is plus 2. One lithium is existing only in plus 1 state. So which is differed here? Charge is differed. So which is the common ion now? O minus 2 is the common ion. That is the thermal stability of compound having monoatomic anion. Monoatomic anion is there. There you have to compare lattice energy. Lattice energy is directly proportional to product of charges. Product of charges, where the product of charges is get? 2 into 2 is 4.
B.
1 into 2 is 2. So obviously BeO. So BeO has more thermal stability. Based on that only, group 2A oxides are more thermally stable when compared to group 1A, because lattice energy is directly proportional to thermal stability, and lattice energy is directly proportional to product of charges and inversely proportional to size of ions. Li2O less stable when compared to BeO, Na2O less stable when compared to MgO, K2O and CaO, CS2 and BaO same order. Yes or no? So in this, if you try to compare BeO, MgO, CaO, SRO, BaO, so what is the common ion? O minus 2 ion. Here H minus ion. Here F minus ion. All these are monoatomic anions. Therefore, thermal stability is directly proportional to lattice energy, because for monoatomic anions, thermal stability is directly proportional to lattice energy. For polyatomic anions, thermal stability is inversely proportional to polarizing power. Now, if you try to compare, charge is same, plus 2 everywhere, plus 2 minus 2, plus 2 minus 2. Lattice energy is inversely proportional to size. So where you have greater size, BaO, there you have less lattice energy, obviously less thermal stability. So BeO is more thermally stable when compared to BaO based on this order. Similarly, LiH to CHH, LiF to CSF. Got it or not?
Yes, sir.
Thermal stability is directly proportional to lattice energy. If you are trying to compare between 1A and 2A, charge is differed. So charge is the dominant factor. Charge is differed as well as size is differed. Both are differing whenever you are trying to compare 1A and 2A. When charge is varying and size is varying, which is the dominant factor? Charge is the dominant factor. When charge is not varying, only size is varying, then based on that only you have to compare. Based on size only you have to compare. This is the order of thermal stability. Respect to metal carbonates heating effect. Heating of metal carbonates, like what are the respect to metal carbonates you are going to heat? Metal carbonate, if you try to heat, you will get metal oxide and CO2. This is the reaction happening. For what? Carbonates of sodium, potassium, rubidium and cesium do not decompose. Remaining all metal carbonates upon heating form metal oxide and carbon dioxide is going to be evolved. Whereas the carbonates of sodium, potassium, rubidium and cesium, they only melt. They only melt but do not decompose. Okay. CaCO3, if you try to heat, you will form CaO and CO2. Only lithium and group 2A. All group 2A and lithium, all group 2A and lithium carbonates upon heating forms respect to oxides and CO2 gas is evolved. Is that clear or not? All group 2A and lithium upon heating, all group 2A and lithium carbonates upon heating form oxides and CO2 is going to be evolved. Heating of metal carbonates, sodium, potassium, rubidium, cesium, you cannot heat them and decompose. You can only melt them. Heating effect of metal hydroxide. All metal hydroxide, if you try to heat, you will get respect to metal oxide and water. Again, hydroxides of sodium, potassium, rubidium and cesium do not decompose. Remaining all hydroxide, you will get what? Lithium and group 2A hydroxides. They will form respective metal oxide. Along with that, water is obtained. Previously, what is obtained? If you heat carbonate, metal oxide and
CO2.
carbon dioxide. Metal hydroxide, if you try to heat, metal oxide and H2O. Metal oxide and H2O is obtained. This is the heating effect of metal hydroxide as well as respective metal carbonates. You can also heat metal bicarbonates. You can also heat metal nitrates. We'll see all those cases. Heating effect of metal bicarbonates. If you heat metal bicarbonate, you will get CO2 and H2O both. But again, bicarbonates of both group 1 and group 2 decompose on heating to form carbonates, water and respective carbon dioxide. Both all like a group 1 and group 2 bicarbonates. No exception. Bicarbonates of both group 1 and group 2 decompose on heating to form carbonate, water and carbon dioxide. That is how we produce Na2CO3. Upon heating NaHCO3 only, you form Na2CO3. With respect to bicarbonate, you do not have exception. But for carbonate and hydroxide, what I have told you, lithium and group 2A carbonates upon heating form oxide and CO2. Lithium and group 2A hydroxides upon heating form oxide and H2O. Group 1A and group 2A bicarbonates upon heating forms carbonates and water and CO2. Nitrates also we can have the exception. We'll see the exceptions of nitrates like lithium and group 2A will produce two paramagnetic gases. For lithium and group 2A metals, metal nitrate upon heating, lithium and 2A, metal nitrate upon heating form metal oxide plus NO2 plus O2. NO2, if you try to draw the Lewis dot structure, N double bond O, NO with one odd electron nitrogen. O2 will have oxygen, double bond oxygen with a O2, oxygen, double bond oxygen with two lone pairs of electrons on each oxygen. But if you look at the pi-star anti-bonding molecular orbital of oxygen, it has unpaired electron. So NO2 and O2 both are paramagnetic in nature. Nitrates of group 2A and lithium produce two paramagnetic gases, that is NO2 and O2 upon decomposition. If you go with the examples, CaNO3 taken twice, group 2A nitrate, it forms CaO plus NO2 plus O2. LiNO3 lithium nitrate forms Li2O plus NO2 plus O2. Two types of gases are going to be obtained. Whereas this is for lithium and group 2A nitrates. Sodium, potassium, rubidium and cesium, those nitrates can also be heated and you will get different other scenarios. What are those obtained? We'll see now. Sodium, potassium, rubidium, cesium, these nitrates can also be heated under two different conditions. Low temperature and high temperature will have different types of gases. Low temperature you will get metal nitrate to metal nitrate and half O2. High temperature you get metal oxide and N2 and O2. N2 is diamagnetic in nature. Diamagnetic, no unpaired electron. O2 is paramagnetic. If you try to heat metal nitrate at high temperature for sodium, potassium, rubidium and cesium, you get one diamagnetic and one paramagnetic gas. Whenever you try to heat lithium or all group 2A metal nitrates, you will be getting two paramagnetic gases. Those are NO2 and O2. Example, if you try to take here, if you try to take an example, you heat NaNO3 sodium nitrate. Sodium nitrate upon low temperature it forms sodium nitrite and half O2. At high temperature it forms Na2O and N2 plus O2. These metal oxides are going to be formed. Along with that, N2 and O2 is released. Is that clear, students? Is everything clear with respect to
Yes,
heating
sir.
effect? We have heated respective carbonates, hydroxides, bicarbonates and nitrates. Nitrates, carbonates and bicarbonates will have differences. Like for sodium, potassium, rubidium, cesium, we have different. And for lithium and group 2A, we have different type of products obtained. But for bicarbonates, upon heating, you will get carbonate, plus CO2 plus H2O, both for group 1A as well as group 2A. Okay. And then the last point which you can think of is melting point. Melting point means what? The temperature at which a solid starts melting. How many types of solids are there? Covalent solid. Crystalline solids are classified into how many types? Covalent solids, ionic solids, metallic solids, molecular solids. 4 types are there. Types of solids, types of crystalline solids, covalent solid, ionic solid, molecular solids, and we also have metallic that was not given here. Because in metallic salts we have metallic bonding majorly. Covalent solid at melting point, covalent bonds weaken. Ionic solids at a melting point, ionic bonds weaken. Molecular solids means hydrogen bonding solids, polar bonded like polar molecular solids, non-polar molecular solids, or hydrogen bonded solids. These are the different example. Covalent solids means you have diamond, graphite, B4C, SiC, SiO2. Ionic solids, NaCl, KCl, Al2O3. Molecular solids, solid CO2, H2O, I2 as well as CH4. These are the respective molecular solids. What is the order of melting point? If you try to compare,
Decreases down the road.
yeah, if you try to compare covalent solid, ionic solid, and molecular solid, what will be the order of melting point?
Ionic solid, covalent, and molecular.
Sure. Covalent solid diamond. 3D networking. The covalent solids will be having extremely high melting points because of 3D structure. Covalent solid will be having the highest melting point, then ionic solid, then molecular solid. Order of melting point, covalent solid will be having the extremely high melting point, then ionic solid, and then you will be having respect to molecular solid. Again, the melting point also decided based on the type of ions present. Like how we decide thermal stability, in the same way melting point is also decided. Melting point of ionic compounds, if you are trying to compare, if common ion is group 1 cation like Na plus, K plus, Rb plus, Cs plus, or H minus, F minus, O2 minus, N3 minus, C4 minus. If these are the common ions, then melting point is directly proportional to lattice energy. If common ions are group 1 cations or respect to H minus, F minus, O2 minus, N3 minus, C4 minus, then melting point is directly proportional to lattice energy. If any other type of ion is there, if any other type ion, melting point is inversely proportional to polarizing power. Yes or no? If a common ion is group 1 cations, Na plus, K plus, Rb plus, Cs plus, not La plus, or H minus, F minus, O2 minus, N3 minus, C4 minus, melting point is directly proportional to lattice energy. If you go with this, thus due to decrease in lattice energy, the order of melting points are, you compare AlF3, Al plus 3, F minus, Mg plus 2, F minus, Na plus, F minus. Lattice energy is directly proportional to charges. Where charge is dominant? Al plus 3. So there lattice energy is dominant. Common ion is what? F minus. Common ion is F minus. So lattice energy is, melting point is directly proportional to lattice energy. So aluminum fluoride, magnesium fluoride, sodium fluoride, if you compare the melting point, you have to compare lattice energy. So AlF3, because of higher lattice energy, it will have higher melting point. Then magnesium fluoride, then sodium fluoride. If you go with lithium to cesium fluoride, F minus, F minus, F minus, F minus, F minus. Everywhere we have same F minus ion, common ion is F minus, and charge is also same everywhere. Li plus, Na plus, K plus, Rb plus, Cs plus. So lattice energy here you have to take inversely proportional to size. Where the size is great, Cs plus, there you will have less lattice energy. Lesser the lattice energy, lesser the melting point. So lithium fluoride is going to have the highest melting point, then sodium fluoride, then potassium fluoride, then rubidium fluoride, and then cesium fluoride. Is that clear or not?
Yes, sir.
Sir.
Yes, sir.
All these after the commercially important compounds, after cement, whatever the discussion we are doing, you read it again and again. That will be important. Melting point, if any other common ion is there, like except the Na plus, K plus, Rb plus, Cs plus, or H minus, F minus, O2 minus, N3 minus, C4 minus, then melting point is inversely proportional to polarization. You try to compare this. Which of the following has least melting point? What is the common ion? Ca plus 2 is common ion. Common ion is not the Na plus, K plus, Rb plus, Cs plus, or H minus, F minus, O2 minus, N3 minus, or C4 minus. Then how to compare melting point?
Polarizing.
Size.
Melting point is inversely proportional to polarization. So everywhere you have Ca plus 2, Ca plus 2, Ca plus 2, and Ca plus 2. Where the polarization is going to happen greatly?
Fourth option.
So greater the polarization, lesser is the melting point. So which of the following has least melting point then?
Fourth option.
Option 4.
Ci.
Yes or no? Ca(I2) because I minus because of large size, the electron density can be easily polarized. Because of easy polarization, the melting point is going to be inversely proportional to polarization. So melting point is going to be least. Right, students? So this is all about your S block. Next classes we will be discussing about P block and all. Thank you all everyone. Bye.
Thank you, sir.
Thank you,
Thank you.
sir.
Thank you, sir.